Forget silicon, what if a computer could think with living cells? Because scientists are already building computers from biology. One of them actually learned to play Doom. This sounds like science fiction, but it's real. Researchers are experimenting with living biological systems. But how?
Because what we're looking at today is honestly one of the most mind-bending and kind of unsettling things happening in science right now. We're taking a trip into the laboratory at Cortical Labs, where a computer is actively playing the 1993 classic video game Doom. Now, on the surface, it looks like a standard automated speedrun, right? But the reality behind that screen is vastly, vastly different.
So that brings up the big question. Who is actually playing this game? Well, there's a really disturbing twist to our mystery here. There isn't a person sitting at a keyboard, and it's not some standard AI algorithm either. Instead, there's a player trapped inside, and it's made entirely of living human brain cells. I know, it sounds literally like science fiction, but this is happening right now. The cells inside the system are the ones actually playing the game.
And the scale of this is wild. 200,000. That massive number represents the exact amount of living human neurons that researchers have wired together to create this biological computer, which they call CL1. These aren't just simulated nodes in some software program. We're talking about actual, physical, human cells spread across a bed of electrodes, actively processing information to navigate those pixelated hallways of doom.
Section 1. The AI Energy Crisis. So you're probably wondering, why on earth would anyone build a computer out of human flesh in the first place? Well, we have to look at the massive electricity panic happening in the AI industry right now. We are hitting a major bottleneck in tech, and it all comes down to the sheer, unbelievable amount of power required to keep our modern machines thinking.
It basically boils down to efficiency. On one side, we have AI data centers. Tech companies are frantically signing deals to lock up huge chunks of the power grid. They're literally restarting old nuclear power plants that were shut down years ago just to power their AI models. But then, on the other side, we have the human brain. Your brain effortlessly does incredibly complex learning and problem solving on about 20 watts of power. To put that into perspective, that's the equivalent of a dim light bulb. And the urgency here is being driven by the number 6. AI computing power requirements are roughly doubling every 6 months. Think about that. Almost nothing in the physical world grows at that kind of breakneck speed. We simply cannot build new power plants fast enough to keep up, which creates this massive, growing gap between what AI needs to function and what our grids can actually supply. So it's no longer just a race for smarter software. It's a desperate race for electricity. Section 2, the road to biological computing. So researchers obviously looked at the unparalleled biological efficiency of the brain to try and solve this energy crisis. But getting from acknowledging how efficient the brain is to actually having a dish of cells playing a video game, that required taking a few bizarre, totally unprecedented steps in the lab.
This definitely didn't happen overnight. If we look at the timeline, back in 2008, scientists grew a sheet of rat neurons and hooked them up to a robot, basically letting those crude biological signals drive it around. But the real game changer hit in 2013 with the Yamanaka cell reset. A scientist figured out how to take a regular adult cell, like a piece of skin, and completely reset it into a blank state so it could be grown into a human neuron. You no longer needed brain tissue. You could just use skin. By 2022, Cortical Labs combined this with 3D cell organization to create DishBrain, which successfully learned to play Pong. And that brings us to today, to CL1, utilizing 200,000 human neurons to play Doom.
Section 3, how to teach a neuron. Now, this incredible timeline brings us to a massive, incredibly practical hurdle. How exactly do you teach a blob of brain tissue to play a game? You can't speak to it, you can't show it a YouTube tutorial, and you certainly can't just hand it a treat when it does a good job.
The secret is rooted in this biological concept called the free energy principle. Basically, it suggests that every living thing is fundamentally driven to avoid surprises. To a cell, chaos and unpredictability are incredibly stressful because out in nature, being surprised usually means you're in danger. Neurons absolutely hate unpredictability chaos. They want their environment to be steady and predictable to ensure they survive.
So, scientists gamified that exact survival principle by tying the game's outcomes directly to electrical stimulation. If the cells in the dish miss the target or take damage in Doom, they are blasted with scrambled, random, stressful noise. But if they successfully navigate and survive, they're rewarded with a predictable, calm, steady signal. It's wild because the cells don't know what Doom is. They are simply trying to make the painful chaos stop.
Section 4. Inside the Doom computer. Okay, to actually facilitate this complex interaction and get these cells to play Doom, a developer named Shankala had to build a very specific, carefully designed architecture. Because, let's be real, it's not just a brain floating in a jar magically playing a game on a monitor. This system actually requires a hybrid three-part architecture. Step 1 is a normal computer chip running an AI. This acts as the watcher, reading the screen and deciding when to reward or punish based on the gameplay. Step 2 is a translator sitting right in the middle, passing those messages back and forth. And step 3 is the flat grid of 200,000 human cells that receive the signals and react. So the traditional computer is actually doing a lot of the heavy lifting here to manage the environment. Now, because that AI chip is so involved, a very natural doubt pops up. Are the cells really doing anything, or is the computer just faking the whole thing? Well, to test this, the developer took the human cells out and replaced them with pure random noise. And when he did that, the learning process completely stopped. This proved that while the traditional AI manages the environment, these living cells are doing a small but highly real piece of the actual computing work. And because of those massive power differences we talked about earlier, this isn't just a quirky science experiment anymore. It is a rapidly growing industry. A Swiss company called Final Spark is already turning this into a subscription business. They're literally renting out 16 human mini-brains over the internet to clients around the world. Why? Because these biological mini-brains consume up to 1 million times less power than traditional silicon chips. The financial and environmental incentives to scale this whole thing up are absolutely massive. Section 5, the sentience question. But as this tech scales up from flat dishes of 200,000 cells to fully connected 3D biological brains, we are forced to confront a profound and frankly chilling ethical complication. We aren't just playing with silicon anymore, folks. We are playing with the fundamental building blocks of human life. Renowned neuroscientist Mark Solms offers a perspective here that kind of shifts everything we think we know about consciousness. He suggests that feeling doesn't require a highly intelligent, fully formed brain. Instead, he argues that feeling comes directly from the basic evolutionary drive to avoid chaos and stay alive. And the terrifying part? That drive to avoid chaos is the exact fundamental mechanism we are using to train these cells with electrical noise. And look, history shows we are notoriously terrible at recognizing when something is aware. In 2006, scientist Adrienne Owen studied a patient deemed completely vegetative. But when she was asked to imagine playing tennis, her brain scans lit up exactly like a healthy person's. She was fully awake and aware, just trapped. Later studies actually found that 1 in 4 patients written off like this are actually conscious. So if we can completely miss full consciousness in a human being lying right in front of us, what chance do we have of spotting it in a clump of cells in a lab? This brings us right to what philosopher David Chalmers famously coined the hard problem. We can map every single cell, every electrode, and every signal in this biological computer, sure, but that physical map still cannot explain how or when an actual feeling emerges. When those cells back away from the stressful, scrambled noise of taking damage and doom, it could just be a cold, automated reflex, or it could be genuine, trapped suffering. And from the outside, we have absolutely no test to tell the difference. Remember, these cells started as ordinary skin from a real living person, and they've been transformed into an entity whose entire universe consists of avoiding stressful electrical shocks while navigating a 1993 video game. So I'll leave you with this final, haunting question to consider the next time you hear about the wonders of biocomputing and the energy-saving future of AI. Are we creating tiny pieces of human beings whose entire existence is feeling pain inside a violent video game just to save electricity? Think about that for a bit. Thank you so much for joining me for this explainer.